All right, how's stuff going? I should give bonus points for the 6 people who are here today. Yeah. All right, so questions. So tomorrow is an open lab, so I will be here. I won't be lecturing on new material, but if you want to come in and work on code, talk about questions, go through debug, look at PA3, whatever, I'll be here. Same thing at the 10 o'clock session. So it's just kind of a drop-in and work for free space to use as you see fit. But hopefully to make good progress on PA4.
These classes slowly kind of shrunk in size.
I keep going back and forth and debating whether to stop posting videos or start taking attendance or just not worry about it. Or give extra credit. The thing is, historically, the people who are coming to class generally do better anyway. So there's kind of a built-in extra credit already, but I don't know what to do about it, but I'll make some decisions for 223 for sure.
I mean, you definitely have perfect attendance for the test.
Yeah, and I have pretty close to perfect attendance when I actually take attendance, but I don't know. I could give tests every day. That would be a good solution.
Or just daily tests or something.
Yeah. All right. So any questions? So let's trace through some of this recursive stuff one more time. And again, this is something you don't necessarily want to be thinking too much about while you're writing recursive code or while you're debugging it. But it's useful to work through this sometimes to kind of see what's going on, just to sort of help you believe that recursion is actually working. And you know, we want to understand things usually. That's our nature. So it's good to have seen this. Let me start with the traverse function. And let me describe a little what happens when we call a function from another function. So we know from talking about stacks and maybe from 270, here's our main program. And it's doing some stuff. And at some point we say, let's call this function traverse. We'll pass it a root, and we want it to print out, say, the left node right traversal of our tree. And then there's some stuff that comes after here. Okay, at an assembly language or machine language point of view, what happens when we call this function is we basically do a goto. We basically branch to wherever this is in memory. So traverse starts at some location in our program memory. We basically change the CPU's program counter so it says start executing these instructions in this function we call traverse. But before it does that, it looks at the address of this instruction following the call and it saves that somewhere. So that eventually when traverse says return, it jumps back to this spot right after the call. Okay, and we also know probably that this is saved on the stack. So we have this stack in memory, and there's various stuff on there, and at some point we have the top of stack. And when we make this function call, this address gets pushed onto the stack, and the top of stack moves. And whatever else happens on the stack, this return address is saved right here. We can push and pop a bunch of things on the stack. It's all going to affect stuff down here. This location is saved. We're running inside traverse. When we say return, what does it do? It looks at what's on the top of the stack. It moves the top of stack back to here, and it jumps to this address, which is this instruction right after the call. That's how we get back from the function call. Okay, so we've talked about that. We've seen it. What we haven't said, though, is that in reality, when we make a function call, we save the address on the top of the stack, but we actually allocate a bunch of space on the stack for local variables. And the top of stack will actually move down here. And now we have a bunch of memory which is free. which we use for the local variables inside this function that we called. So if we have an integer I or we have a struct node star temp, those are stored inside the stack space. And the advantage of that is twofold. One, when we return from our function, our stack pointer moves back to here. All of that space is free now. It's available for other things to use on the stack. But two, if our traverse function makes another call to traverse, what happens? The stack pointer is moved down to here, and all of this is used for local variables in that new call to traverse. And they're completely separate from the local variables in that first call. Okay, this is what makes recursion possible. Because even if a function is calling itself, it gets an entirely new set of those local variables. So this struct node star temp in the called version of traverse is different from the one in the original. And it's different from what might have been a struct node star temp inside main. Right? And it can call itself 20 times, and there are 20 different copies of this struct node star temp sitting at 20 different locations in memory. And when this call finishes and it returns, struct node star temp is whatever it was before that call happened. So making a recursive call to a function basically picks up your whole context and preserves it. And it says, we're not going to use this for now, but when we return from the call, I want everything to look exactly like it did before the call. Okay, that's sometimes called a call frame. It's a chunk of memory that lets you save not only the return address to get back to a function, but the whole context, the local variables, where you were in that function, all this other information are saved. So I have a stack of call frames we're going to use to play with some traversal. So let's traverse a tree. How many call frames do I have left? Oh, I got a few. Okay, so this is page 1. And this is called from main. And the idea is that inside main, we're going to say traverse. Root, where our root is the root of a tree that looks like, let's say this. All right, so we make this call to traverse. This is the mind of the computer as it's executing this traverse function. It was passed an argument root, which looks like this: 20, 10, 5, 15, 30. And the code starts to execute. So it starts to execute this first instruction, which says, is the root null? Well, it's not. It points to a node containing 20. So nothing happens there. Next it says traverse root arrow left. This is the root arrow left is this tree. So this is calling the traverse function with this tree as its argument. Okay, so we're going to start a new call frame, a new section of the stack. It's called from page 1, and the root that we're passing to this is 10, 5, 15. And we're in the middle of doing this traverse. Okay, this gets pushed on the stack. That's right here. And now the CPU is like, oh, I have to execute this function traverse. Here's my root. Okay, I can do this. Is the root null? No. Okay, let's traverse root arrow left. So it looks at root arrow left, that's a tree containing just a 5, and it makes a call to traverse. Okay, this will be a new call frame. It's called from page 2, and the root looks like this. All right, this goes on our stack. And now we're executing this function traverse where the root is equal to just 5. So first instruction is root null. No, it's not, so we don't return. Next, traverse root arrow left. Well, root arrow left is null. Okay, so it's going to make another call to traverse. This is call frame 4. It's called from page 3, and our root is null. This goes on the stack. Okay, well, we start executing the first instruction. Is root null? Yes, it is. We're going to return. Okay, when we say return, what do? We go back to where we were called from, which was page 3. So we jump back to page 3, that's on the top of the stack. We pop that off. We just got back from our call to traverse, root arrow left, we're done with that. Now we say print root arrow data. So let's make an output area. And this is what's actually being output by your program. First thing it's going to print is root arrow data, that's a 5. We're done with the print, now we're going to traverse root arrow right. Well, root arrow right is null, so we'll make a call to frame 5. It's called from page 3, and our root is null. And first statement says, is the root null? Yes, it is. It'll return. And we're done. And now there's a return statement at the curly bracket. Okay, what we've just done is we finished a complete execution of the traverse function for this tree. And the output that was produced was a 5. Okay, we're done with this call. We're going to return. Where do we return to? We return to call frame 2. Well, that's right on the top of the stack, so we pop the top of the stack, and we're back from our call to traverse. We finished that. Now we say print the root data, that's a 10, so we'll output a 10. That's done. Now we traverse root arrow right, which is a 15. So we make a new call. So this is, I don't know where we're up to, let's say page 6. Called from page 2, thing we're traversing is 15. This gets pushed on the stack. Alright, is the root null? No. Traverse root arrow left. Well, and I won't keep doing this one, but you know, we'll make a call with a null and it will decide it's null and it won't do anything. So that's a no op. Print the root arrow data, that's a 15. So it prints a 15, that's done. Traverse root arrow right, that's going to traverse null, won't do anything. Now we're done. What did this call do? It traversed the tree that looks like this. That's what printed this 15. We're going to return back to call frame 2. Okay. We don't need to know what call frame 2 is. It's on the top of the stack. We pop the stack. We just finished this traverse of root arrow right. Now there's this return statement here. And what have we done? We finished executing the traverse statement on this tree. What did it print? 5, 10, 15. We return, where do we return from? Page 1. Where's page 1? It's right on the top of the stack. And we just finished traversal of root arrow left. That was the 5, 10, 15. Now we print root arrow data. That's going to be a 20. So that's done. And now the last statement, traverse root arrow right. That's a node containing a 30. And same thing. So this is called from page 1. That goes on the stack. Our root is just a 30. Is the root null? No. We'll traverse root arrow left, which will be null. It won't do anything. We'll print root arrow data, which is a 30. We'll traverse root arrow right, which is a null, and it'll come back right away. And now we return. And we return to page 1, which is on the top of the stack. And we just finished traversal of root arrow right. And there's a return here. And where do we return to? We return to the main program. This goes off the stack, and now we're back to executing whatever our main program was doing. And we just finished this traverse of root, and that's the output that was produced. Okay, that's the way that the recursion winds up and then winds down. It's definitely magic. And again, you don't need to think about this when you're writing the code. Right? If you're writing a left node right traversal, it's just those 4 statements. Right? You have to have faith that this is going to do the right thing. And if you believe that, then this will do the right thing. Okay? And this will do the right thing if this does the right thing on a smaller tree, right? This is inducting downward to the base case where your tree is null. And if the tree is null, yeah, this does absolutely the right thing. It prints nothing. Don't have to recurse to know that. But if an empty tree traverses correctly, then a tree with one node will traverse correctly because you know, the traversal of the left will be null. It won't print anything. It'll print the root. It won't do anything on the right. And if a tree with just a root node prints correctly, then a tree with one level below that will print correctly also. So you can induct back up if you like.
It makes me really appreciate the tedious work that a computer does.
Yeah, computer's life is kind of terrible. And most of the time computers are doing nothing. They're just twiddling their thumbs. They're usually just like loop, branch to loop.
True, yeah.
Because there's just not enough to do, you know, a few billion things a second.
And this has technically 6 null nodes that has to turn into
Yeah.
trees.
Yep.
Check.
Yeah. It would be even worse is like being hired as a human to do this work. That's like a Kafka novel or something. All right, so let's look at doing insertions. Let's build a tree. So let's start off with root equals null. And let's say root equals, I think I called it insert, root, comma, let's insert a 50 into our empty tree. Alright, so this is a function call. I'm calling this function insert, which I happen to have here. These should be root, and that should be temp equals malloc. So we're a kind computer that corrects the programmer's code for them. Alright, so this is page 1. It's called from main. That's up here. Our root is null, and the number we're inserting is 50. So we called insert root, which is null, number is 50. Okay, so this is the insert code we've talked about, right? If the root's null, make a new node and return that. Otherwise, insert either on the right or the left, depending on how you compare it to the root node's data. All right, so first thing we do in the insert routine, we see if the root is null. Yes, it is. So we make a new node called temp. We set its data equal to the number. We have nothing on the left and right child, and we return that as the function value. So our main program called insert, it gets back a tree containing just a 50, and it sets root equal to that. So now root is this single noded tree. Okay, that worked fine, not too startling. Let's insert something. Let's insert a 70 into this tree. So we're going to make a call. This is page 1. It's called from main. We're calling it with root looking like this, and our number we're inserting is 70. Okay, is root null? And let me make my typo fixes. Is root null? No, so there's nothing to do there. Is our number bigger than root data? Yeah, our number 70, the root data is 50. Yes, it is. So we're going to execute this block of code. So we're going to call insert on root arrow right, which is null, and we're going to ask to insert the number 50. Okay, so this is called from page 1. We're trying to insert the number 70. Our root is null because we're inserting into root arrow right. This will make a new node, set its data value equal to 70, and return that. So the return from this call to insert is this tree containing just a 70. And this call to insert said make a new node temp equal to that return value. So temp looks like this. And then we say root arrow right equals temp. So root on the right side picks up that 70. And that finishes this, and we return root as the return of this call to insert. Where do we go back to? We go back to main. And now main says root equals the result of insert. So now root looks like this. All right, one more. Let's insert a 60. So new call frame. This is page 1. It's called from main. The root that we're passing to it is main's root, which looks like this. We're inserting the number 60. Fix our typos. All right, is root equal to null? No. Is our number bigger than the root data? The root data is 50, our number is 60. Yes, it is, so we'll execute this block. And this says insert into root arrow right the number num. Well, root arrow right is just this node containing a 70. So we make a new call. So this will be page 2. It's called from page 1. The root looks like this. We're inserting a 60. This goes on the stack. All right, is the root null? No, so we skip that. Is our number bigger than the root data? No. 60 is smaller than 70, so we don't do this. So we do this instead. Insert a 60 into root arrow left. Okay, root arrow left is null, so we're going to insert 60 into this null tree. We've already done that a few times. We know the return from that's going to be just this thing that looks like that. And we set temp equal to the result of that insert. So temp is going to look like this. And now we're going to say root arrow left equals temp. Okay, here's the root, so we're going to set its left child to be 60. And we're done. And we're going to return this root, the root of this tree, as a return value of insert. And we were called from page 1. Okay, so we popped page 1 off the stack. And we were doing this. We were calling insert, and we're going to set temp equal to the return value, which is this thing here. So temp looks like this, 70, 60. That's the return of insert. And now we say root arrow right equals temp. So our root is a 50. We're going to change its right child to be the root of this tree, which is 70, 60. And we're done, and we return that back to the caller, which was main. And main said set root equal to the return value, which is this. So now up in main, root looks like this, 50, 70, 60. And that's exactly what it should look like after we insert those nodes in that order. So you can do this when you get kind of stuck in a really bad way. Like, I really don't get what's going on here, right? You can go back and you can work through it at this level and sort of break the log jam sometimes. But if you try to think about it like this while you're writing the code, it'll probably just make things more confusing. Okay, but you can do this. And you can do this when you're debugging, but it's not pleasant. So if you've got your code and it's not doing the right thing, you're trying to insert a 60 and it just doesn't show up, this may not be the way to think about it, but you may have to. So suppose this is my tree and I try to insert a 60 and it's not working. Yeah, go into GDB, and you're going to need something like this, right, or sections of a whiteboard or color coding or something, and work your way through this, right? And I would probably say, you know, okay, so I'm inserting a 60 into this tree. Make this call to insert, and when you come back, see what temp is. And see if temp actually looks like a 70 with a 60 on it. If it doesn't, then something went wrong in that call to insert. Now you just have to debug that call. Right, so go back, and this time step into the insert function, and you'll call insert with just a 60, right, and trying to add one node to that. Okay. So debugging recursion is tricky. The good news is that a lot of times the recursive stuff is pretty small, right? And the part where it's calling ourselves is usually not where the issue is. It's usually what we're doing with a return value or what we're passing to the recursive call. It's usually not an issue with, you know, how all of this is playing out internally. All right, so let's do deletion. And let's start with whatever. Yeah.
Just remind me, the algorithm you gave us for deleting node was preferring to take the largest number from the left.
Mm-hmm. Yeah. Yeah, you're required to use the largest number from the left. All right, that's a bigger tree than I should have made. Let's delete the 20 from this tree. So I'm passing root, which is, you know, the address of the 100, but we can think of it as this whole tree. So this is our main program. We want to delete the 20 from this tree. So we make a call to delete. We're called from main. Here's page 1. We're deleting 20, and our root looks like this. And I won't draw all of this out. Maybe I will. Yeah. The root is just a location memory, yeah, it's just an arrow. But we're thinking of it as, you know, all of that, yeah. That's that double think thing. Alright, so we're trying to delete 20 from this tree. We call the delete function. First thing it says, is the root node equal to the data? And it's not. Our number is 20, the root node's 100, so we're not going to do this. Okay, if our number is smaller than the root node data, which it is, 20 is smaller than 100, so we're going to execute this block of code. So first thing we're going to do, we're going to call delete on the left subtree. So we're going to make a new call frame. So this is page 2, called from page 1. We're still trying to delete 20, but we're being passed the left subtree, so the root looks like this. Okay, there's the root of the tree. This is going to go on the stack because we're making a call. All right, is the root data equal to the number? Yes, it is. So we're going to do stuff. What stuff do we do? All the stuff we talked about yesterday, okay, which we'll pseudocode after this. But basically, we're going to go to the left subtree. We're going to find the largest thing in that left subtree. That's going to be our 18. We're going to move that to the root, and we're going to have the node before the 18 adopt 18's left child, which was the 17. So we're going to do stuff. We're going to create a new tree that looks like this. We're going to call it temp. It's going to have an 18, a 10, a 5, 12, 15, 14, 17, 30, 25, 40. So that's the stuff we went through yesterday. Okay. And in the end, this call to delete is going to return this as its value. So the root of this tree, 18. We return to page 1. That's the top of the stack, top of the stack. We were in the middle of this. We were setting temp equal to the return value from delete. So temp is going to look like just what we returned. Temp's going to be an 18, a 10, a 5, 12, 15, 14, 17, 30, 25, 40. So this is done. And then we're going to say root arrow left equals temp. Well, root is this node right here. We're going to set its left child to be temp. So 100 is going to look like this on the left. The right child's not going to change. And then we're going to return root. So we go back to main, and after we get back to main, root is going to look like that. So if we said root equals delete all that, now root looks like 100, 200, dot, 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 18, 30, 40, 25, 10, 12, 15, 17, 14, and 5, right? And this is that original tree with the 20 removed. And the stuff above 20 doesn't change, right? So if we make a bunch of recursive calls to get down to the point where the root node is equal to the thing we're trying to delete, all that stuff above is going to be exactly the same afterwards. But the point where the number actually appears, that's where the tree is going to change. And in that case, the 20 got replaced by the 18. All of this stayed the same. This stayed the same, except that 15 adopted the 17. So we get back and we remove 20 from the tree.
It seems like this is using deletion, but just replacement.
Yeah, yeah.
Like even at the bottom of the city, like delete that, so it's technically replacing 17 with null. So would that not be true?
So we're replacing 15's right child with null. And then we're freeing 17, putting it back in the memory pool. Slightly different.
Okay,
Right, the actual change is being made to 15.
I see.
Yeah, that's subtle. All right, is that making some sense? Again, you don't always need to go back to that level, but I'd like to go through it at least once in a while. So let's pseudocode this deletion business. So let's delete a node from the tree. And if we're not deleting the root node, we're going to do some recursion. Okay? We're going to keep calling delete on either the left or the right subtree to move down until we get to a spot where the thing we want to delete is the root of our tree. So I just want to spec out the code for deleting the root. This was what we worked through yesterday. Okay, so delete the root. Well, here's our first edge case. We want to find the largest thing in the left subtree. If there is no left subtree, we can't find the largest thing in the left subtree. So in that case only, what we can do is we can change the root to simply be the right child of the root. Okay, that'll remove this, and the next largest thing will be this root. So if root left is null, then free the root and return the right subchild of the root. But you got to watch the order of this. Yeah?
So what happens when the right subtree is also null?
Then we're just deleting the root. But we would just return the root right subtree, which is null, so we'd return an empty tree.
Oh,
So that actually works out the same. All right, so you got to use a temporary pointer. You can't free the root and then talk about root arrow right. And we can't return and then free the root, because once we return, we're not executing any more code in here. So, you know, set a temporary equal to root arrow right, and then free the root, and then return the temporary. And that struct node star temp equals root arrow right. Right? There's no mallocing to be done here. This is just a pointer to a struct node, set it equal to what root's pointing to on the right, free the root, and then return temp. Right? Temp's a local variable. Its memory will get released after you return. We're not mallocing anything. We're just saying point to this. All right, so that's one edge case. There's nothing on the left. Otherwise, we have stuff on the left. And we've probably got stuff on the right too. Alright, so our tree looks like this. Here's our root. Okay, I'm going to call something like left subtree equals root arrow left. So this is LST. And we want to find the largest node in this tree, okay, in LST. And there's one edge case to deal with here also, which is, right, the prescription is start from the root and move as far to the right as possible. Well, if there's nothing to the right of that root, then the root is the largest node. So if LST right equals null, then the root's the largest node, and our prescription is take the largest node in this left subtree, make that the new root of the original tree. Well, how do we do that? Simply have it adopt root's right child on the right. So LST right equals root right, and then free root, and then return LST. So if this is our left subtree, and there's nothing to the right of the root, have the root pick up the old root's right child, release the old root, and then return this as the new root. So we're basically just shifting all of this up to take the place of the root. The general case, we have our root, we have our left subtree, and there's data here, and there's data there, but there's also data hanging over here. Right, whatever it looks like. So here's the left subtree. We want to find the largest node in there, and we also want to find its parent. Okay, so we do our usual walk down the list. So prior equals LST, so this is prior, and current equals LST arrow right. So here's current. Okay, in this degenerate case, if we tried to do this code, prior would be this node here, current would be null. Okay, that's why this has to be a special case. Okay, and we want to march this pair down until prior is right here and current is down here. Okay, once we've got that, we're in the situation we were in yesterday. We can make our adjustments and be done. So we want to march prior and current down this chain of right children until current is the last element in that chain. So that suggests while current right is not null. Okay, so what do we do? Well, we set prior equal to current. So this will become T, and then current will be current arrow right. So this will become current. Current right is not null, so set prior to current, current to current right. Current right is not null, set prior equal to current, current equal to current right. Current right is not null, set prior equal to current, current equal to current right. Now current right is null, we'll kick out of the while loop. So once we exit this while loop, what do we got? We've got LST, which is the root of this left subtree. We've got root, which is the original root. We've got current, which is the rightmost node, the largest node in the left subtree, and we've got prior, which is its parent. And now we can just spin the code that we were doing yesterday to make all of our adjustments. So what has to happen? Well, current's going to move up to the root, it's going to abandon its left child. So that's going to get adopted by the prior node's right child. So prior right is going to equal current left. That picks up that child, so it's not orphaned. And then current should become the new root. That's the largest node in the left subtree. How do we make it the root? We said its left child to be here and its right child to be there. So current left equals whatever root current left is, which is also LST, or we could do root arrow left. Current right equals root right. So now this node is pointing to that on the left, that on the right. And then we can free the root because we've already used the information we needed from that. And then we return current as the new root. So that's a tree deletion algorithm. And you can look at the code, but the best way to use this is to try to recreate the code, right? Make sure you understand the algorithm, which is, one sentence, take the largest node from the left and use that as the new root. But then try to understand the implementation of that, the steps you have to go through to make that happen, in particular the edge cases, like there's nothing on the left, or the largest thing on the left is the root, right, or the general case. And then think about the steps you go through in each of those cases to do what that one sentence says, find the largest thing in the left subtree and replace the root with that. And then try to write code to do that. And you should end up with something that looks like this, right? Your own variables, some of the orders can be changed, but effectively this. And then if you feel like gambling, code it up and see what it does. There's a good chance it'll work first time. If it doesn't work, your code may hang. Your code may print out results forever when you try to traverse. If you created a cycle somewhere, your code may segfault. Okay? Your code may work great for a while and then do one of those things. Okay? But code it up and see what it does. And if it looks like it works, then start throwing some test cases at it. Right? Try making a tree that looks different ways. Try deleting the root, try deleting some of the leaf nodes, try deleting things in the middle of the tree. Try deleting every single node from the tree so that the tree ends up being null. Right? This same set of code should work for all those cases. And if it's not working, right, take your code or your pseudocode if you're at the pseudocode point and work through it on a board. Right? Make a tree and then again, switch off your computer science brain. Forget about deletion algorithms. Just follow the code that you've written line by line. And forget the fact that, this should take the largest node on the left and make it the root. Just do what each statement says. write down your variables, and blindly just obey the code. And when you get to the end, if what you have, looks like the Mona Lisa instead of your tree with a node deleted, right? Now go back and turn on your computer science brain and say, what was supposed to happen in each of these steps? And see where things started doing something different. Okay, again, once you get this to work, it's a fantastic feeling. It's like really fun, because then you can insert things, you can delete things, you can do that all day, and it just works. And once it works, you won't be able to imagine a time when it didn't work, because it will seem so obvious to you that this is good code. And that's a fun place to get to, and it's a great place to work from. All right, questions about that? And if we were in a parallel universe, where, I said you have to take the smallest node from the right subtree and use that in place of the root, right? It's almost exactly the same code, but you start off with the right subtree and you move as far as you can to the left, and you take the node prior to that and you adopt that smallest node's right child on the parent node's left subtree, and so on, right? It's just a mirror image of all of this. And for us, we're always doing largest node from the left. But in practice, you might alternate, so that as you delete, first you delete by moving a node on the left, and then you delete by moving a node on the right. And you go back and forth to try to keep things more balanced, depending on how often you're deleting. All right, well, I will be here tomorrow, 10 o'clock to 12 o'clock, open lab. Come in if you want to work on stuff. Bring your code, and we can talk about issues with PA4. We can go back and look at PA3. We can talk about any of the stuff in general. If you don't need any of that, you're free to take the afternoon off from class tomorrow. And then Monday will be a regular class as usual. All right, so I will see you next time.